First, I'd like to thank the University of Missouri, the ICCF Organizing Committee, and the Technical Program Committee. This preliminary study points to the detection of faster-than-light particles in experiments, most of which are LENR experiments. And I wanted to emphasize that this is a preliminary study and there will be speculative elements to this. Unidentified particle tracks have been reported in a number of LENR and other studies. A wide range of track properties are shared throughout diverse studies, including below discharge, electrolysis, transmutation, and electric discharge. My experiments used human hands and no discharges. Also, Bardal et al. Used emulsions with no discharges. 5 out of 8 of these studies mention these tracks as due to the Low-Shack monopole, but with not so much evidence. My tracks replicate virtually all of the tracks found in other studies. The source of the tracks is unknown, but not needed for the analysis of tracks. Let's look at the track properties. The first track property we look at is regular periodic structure. Track A shows one of hundreds of these types of periodic tracks that I found in my own data. Track B is a periodic track on photographic emulsion from Rodionov and Savatimova in autoradiographic emulsion. Track C is a periodic track in palladium deuteride from Rodionov and Savatimova. And D is a periodic track on MDS, a semiconductor detector in Adamenko and Vysotsky. This is a series showing progressive curvature in a non-uniform magnetic field. 4 properties are shown here: periodic structure, track curvature, vertexes, and correlation. If we slice up the 2 outermost tracks from the previous slide and find the difference in angle of the tangent to corresponding segments, the angle is found to be inversely proportional to momentum. This is an example of the two-tailed vertex used for the 18 sample tracks that I look at in my study. And this is the two-tailed vertex. These are correlated random motion tracks. One track can be overlaid upon another and is suggestive of entanglement. Both particles are virtually completely in sync. The tracks here appear to split, and because of the wide range of observed track widths among the studies, a correction factor zeta is used, where W, track width, W equals track width, and W0 equals the minimum measured track width. This is called bundling and splitting. Energy deposition for a given track is found using parameters for Kodak type NTB3 emulsion. We assume 600 electron volts to expose a grain, a silver bromide grain. And we assume a silver bromide gelatin ratio of 85% and a grain size of 0.34 micrometers. Deposited energy for this sample track, which is 13.3 millimeters, is 69 giga-electron volts. Detailed examination of these tracks in applied magnetic fields shows parabolic curvature. Curve fitting of our 18 sample tracks gives an average goodness of fit of 0.997. Momentum is computed using particle coordinates, charge, magnetic field, and energy. Plotting deposited energy, which we assume is about equal to the kinetic energy, against the momentum, yields a cluster of points in the area of the graph where velocity v is greater than the speed of light. Using the standard equation to find mass of charged particle tracks, that is the energy-momentum relation, we find a mass of about 200 mega-electron volts and a very low beta value whose contours intersect nowhere near our cluster of points. So this is using the standard computation. If the particle is a tachyon, we must apply a superluminal Lorentz transformation to the observables. We transform the free particle, the standard equation, the momentum energy relation, to be with the superluminal Lorentz transformation, to find the mass and the beta contours to intersect, and we find them to intersect directly with the cluster of points here. This provides a check and suggests that indeed this makes sense, that the particle is superluminal. Several major searches for monopoles noted that parabolic curvature in an applied magnetic field is a monopole signature. And this is in a parallel applied magnetic field. However, what we're seeing is curvature in transverse to the applied magnetic field. So it's in the wrong plane. But again, applying the superluminal Lorentz transformation to the observable, we find for a very fast tachyon, the magnetic field transforms into an electric field, and the plane of detection is rotated by either 90 or 270 degrees. Therefore, what we can see, we can suggest that we're observing the parabolic curvature of an electrically charged tachyon in a parallel electric field. Continuing with the theme and taking this one step further, as Rakami has shown in his seminal papers, and this is probably the major paper in the theory of tachyons. If tachyons are point-like or spherical in their rest frame, we can transform that into our frame using a superluminal Lorentz transformation, and it looks like a double hyperbolic annulus. If we set these structures in motion along helixes, which are valid trajectories for tachyons, we find that we can simulate many, if not all, of the observed particle tracks. The complicated periodic structure tracks can be simulated by intersecting helically orbiting hyperbolic annuli with a plane. And the research objectives moving forward are to, number one, verify this result. And we want highly calibrated electromagnetic fields and detector response. We want to use high precision microscopy and to analyze this stuff. We want to find the mass, sign of the particle, direction, helicity. We also want to try and figure out what is the particle source. And there are suspected annihilation points at these two-tailed vertexes that we pointed out before, and also suspected entanglement, or highly correlated particles. And then we want to see is it possible to control these particles. So we control the particle behavior, and we're also interested in material interactions. It's very interesting to note about the palladium deuteride, how it's a semiconductor showing particle tracks. And so the implications are that this is the exotic particle approach to solving the LENR issues. And the idea would be that the suggestion is that a tachyon monopole may be acting as a potential catalyst in these reactions. And that's it. For more information, go to my website where I have papers. I'll put up this presentation as well. And thank you.
Have we any questions for Mr. Fredericks?
Yeah,
Yes, Jean-Paul.
Do you know about low shock? Did you hear about low shock magnetic monopole, light?
Yes.
How does it compare to your models?
Low shocks, what I'm using is the Rakami model for magnetic monopole, or for monopole tachyons. And I'm really looking at tachyons as in the classical theory of tachyons of Rakami. That doesn't rule out what Loschak has done. In fact, he does have one solution to his equations that is faster than light. So it's an extremely interesting avenue to pursue as well.
So I noticed you said that it's an electrically charged superluminal particle. If that really explains the behavior of the particle, it makes you suspect that it's actually a magnetic monopole, not just a moving electric charge.
The idea is that it shows up to us in a slower than light frame masquerading as a magnetic monopole. In the faster than light frame, it shows up as an electrically charged tachyon.
Your slower than light frame is the film, though, right? Which doesn't give you any time resolved information.
The film would be a volume element superimposed upon whatever laboratory frame and whatever superluminal frame happened to be coinciding.
You have to get to
Do you have a mass for this particle?
Yeah. The mass, and this is all very preliminary data. The mass that I found using the superluminal Lorentz transformation is 4.5 times 10 to the 14 electron volts per c squared. So it's heavy.
Is the speed you're talking about, is that phase speed or particle speed?
Particle speed.
Any other questions?
Here's the microphone.
On the charts you showed in the first slides, I get what linear scale was on it, but it didn't look like the particles were slowing down. They're very uniform tracks, or was that just looking at a very small portion of the track?
Which tracks are we talking
The
about?
tracks, if it was slowing down, do you think that the tracks would change dimension? The features on the tracks would change dimension. Did you see that?
It's unclear at this point, and this is one of the things that we want to look at, is direction and every parameter that we can get from this data. And I really don't know what direction the particles are traveling in, or exactly what speed they are. I have data that indicates that, for example, with the parabolic curvature, that it should be accelerating in that direction. But that's about as far as I've taken it.
Any other questions? Thank you very much.